All right, AP, let's start on Chapter 3. What we're trying to get out of Chapter 3, at least the first section, explain how it is possible to count the number of objects present in a sample using their weights. Use data from mass spectrometry to identify the elements and masses of the individual atoms of a specific element. Then relate the average atomic mass of an atom to the data generated by a mass spectrometer. And then lastly, define and determine molecular mass and formula mass. So here we go. So counting by weight. So suppose you work in a candy store that sells gourmet jelly beans by the bean because you did not pass AP chemistry. People come in and ask for 50 beans, 100 beans, 1,000 beans, and so on, and you have to count them out. Isn't there an easier way? So assume that all of the jelly beans are identical and that each has a mass of 5 grams. If a customer asks for 1,000 jelly beans, what mass of jelly beans would be required? Each bean has a mass of 5 grams, so you need 1,000 beans times 5 grams per bean, or 5,000 grams, aka 5 kilograms. It takes just a few seconds to weigh out 5 kilograms of jelly beans. It would take much longer to count 1,000 of them. In reality, jelly beans are not identical. For example, let's assume you weigh 10 beans individually and you get the following results. We have 10 different beans here. The first bean is 5.1 grams, then there's 5.2 grams, 5.0 grams, 4.8 grams, 4.9 grams, and so on and so on. If we're going to calculate an average here, we're going to take the total mass of all the beans added together, divide them by the number of beans we're measuring. So it's going to look something like this, and we're going to come out with a calculation of 5.0 grams per bean. So the average mass of a jelly bean is 5.0 grams. Thus, to count 1,000 beans, we need to weigh out 5,000 grams of beans. This means this sample of beans in which the beans have an average mass of 5 grams can be treated exactly like a sample where all of the beans are identical. Objects do not need to have identical masses to be counted by weighing. We simply need to know the average mass of the objects. And for the purpose of counting, the objects behave as though they were identical, as though they each have exactly the average mass. We count atoms in the exact same way. Because atoms are so small, we deal with samples of matters that contain huge numbers of atoms. Even if we could see the atoms, it would not be possible to count them directly. Thus, we determine the number of atoms in a given sample by finding its mass. However, just as with jelly beans, to relate the mass to a number of atoms, we must know the average mass of the atoms. So, for example, a pile of marbles, again, this is just an example. A pile of marbles weighs 394.80 grams. 10 marbles weigh 37.60 grams. How many marbles are in the pile? Well, first we need to establish the average mass per marble. Simple calculations give us 3.76 grams per marble. We simply divide the mass that we've measured by our average mass, and that comes out to be 105 marbles. So, moving on, bringing this same example to the idea of atoms. Recall from general chemistry that the unit used to represent the mass of individual atoms is the AMU, also known as U, or just unit. Okay, so don't be surprised if you see AMU or you see U interchangeably. They mean the same thing. So the AMU, or U, is arbitrarily, again, scientists just decided this. It's not like some thing that was measured in nature. It's arbitrarily defined as 1/12 the mass of a carbon-12 atom. All other atoms are given masses relative to this standard. How do they go about generating this data? Mass spectrometry. The most accurate method currently available for comparing the masses of atoms involves the use of a mass spectrometer. Mass spectrometer first ionizes the atom, creating a positive ion, knocks out one of those valence electrons. It is then accelerated and passed through an electric field. The positively charged ion is then deflected by the magnetic or electric field, meaning the path of the ion changes because of that field. Because the amount of deflection depends on the mass of the atom, meaning the most massive ions are deflected the least, or their path changes the least, accurate values for the relative masses are generated. And so when we're looking at the machine, we're going to look at something that's generally constructed like this. Over here on the left, we have our sample. We shoot it through slits to make sure that we're having a very understood path of the ion. We have positive and negative electric plates here. This is then ionized, pass through these plates, and so there's going to be some sort of deflection, and then there's a detector somewhere, and that's going to measure the magnitude of the deflection. For example, when carbon-12 and carbon-13 are analyzed in a mass spectrometer, the ratio of their masses is found to be 1.0836129. It's very precise machine here. Since the atomic mass unit is defined such that the mass of carbon-12 is exactly 12 atomic mass units, then on this same scale, we're going to calculate the mass of carbon-13. We're going to take that relative mass, multiply it by 12 atomic mass units. That's our standard. It's an exact number, so that two significant figures right there is not changing our value at all. The mass of a carbon-12 atom is exactly 12U or AMU, and the mass of a carbon-13 is 13.003355U or AMU. However, the mass given by your periodic table is neither of these numbers. In the real world, carbon is naturally found as a mixture of the isotopes carbon-12, carbon-13, carbon-14. But these three isotopes are not equally abundant. Carbon-14 is actually extremely rare. It is known that the natural carbon is composed of about 98.89% carbon-12 and just a little bit over 1% carbon-13. If you're doing some math in your head there, the percentage left over of carbon-14 is actually incredibly small. So I'm gonna show you an example of calculating the weighted average mass of carbon. I'm not going to include carbon-14 in those calculations because at this level of precision, it's not going to change the final result. We'd have to use much more precise numbers than what we have access to right now. So that's why you're not going to see carbon-14 in this next example. So using the masses of carbon-12, which is exactly 12 AMU, and carbon-13, which has a mass of 13.003355U, we can calculate the average atomic mass for natural carbon, meaning naturally occurring carbon, like we do on this slide right here. We take the percentage of the 12 AMU carbon, and we're going to add it to the percentage of the carbon-13. Now, the way that looks in terms of calculations, we are going to multiply those percentages as decimals. So the 98.83% becomes 0.9889. We're going to multiply that by 12 AMU. We're going to get that value, and we're going to add it to 0.0111 multiplied by 13.0034. Again, we're rounding here because of precision issues. When we calculate those things out, and remember, I'm not including carbon-14 because at this level of precision, 4 significant figures is not going to change our value, so we're just leaving it out. 12.01 U. In this course, we will call the average mass of an element the average atomic mass, or simply the atomic mass of that element. 12.01 is the average atomic mass for carbon, even though no carbon atom in real life has a mass of 12.01. It's a weighted average. So even though natural carbon does not contain a single atom, what I just said, blah, 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 for stoichiometric processes, when we start doing math and stoichiometry, we consider carbon to be composed of only one type of atom that has a 12.01 mass. This enables us to count atoms of natural carbon by weighing the sample of carbon. So let's see what this looks like. Here's a concept check. I'll give you the answer. Please press pause so you can attempt this yourself before you check out the answer. An element consists of 62.60% of an isotope with a mass of 186.956 AMU and 37.40% of an isotope with a mass 184.953 AMU. Calculate the average atomic mass and identify that element. So using the same process, converting those percentages into decimals and simply multiplying by the mass of that particular isotope, adding those together, I'm going to come up with 186.2 AMU. Now, what is this element? Looking on the periodic table, you're going to find that this is rhenium, Re. Moving on to section 2. I want you to be able to connect the numbers of particles, moles, mass, and volume of a substance to one another, both qualitatively and quantitatively. Basically, convert between all those things: number of particles, moles, mass, and volume. Identify the number of elementary entities in a mole of any substance and calculate the molar masses of elements and compounds. This is basically saying, hey, know what Avogadro's number is and know what it means. Elementary entities, how many particles are in a mole? Okay. And then lastly, weird bullet situation there. Perform calculations involving moles, masses, numbers of atoms, molecules, or formula units. All right, the mole and Avogadro's number. The number equal to the number of atoms in exactly 12 grams of pure carbon-12. I know it's kind of like a weird arbitrary situation, but that's what it is. If you have only carbon-12, okay, no carbon-13, no carbon-14, just carbon-12, and you have exactly, like perfectly exactly 12 grams of it, however many atoms are in that sample, that's defined as Avogadro's number. So that's a mole. 1 mole of anything is 6.022 times 10 to the 23rd units of that thing. Whatever that thing is, that's how many of them there are. And that number is known as Avogadro's number. In other words, 1 mole of carbon has 6.022 times 10 to the 23rd carbon atoms, and it has a mass of 12.01 grams. All right, concept check. Again, press pause so you can try this yourself before I give you the answer. Calculate the number of iron atoms in 4.48 moles of an iron sample. Again, using the molar mass that we get from the periodic table for iron, using Avogadro's number as a conversion factor, we find that it is actually 2.70 times 10 to the 24th iron atoms. All right, section 3. Connect the number of particles, moles, mass, and volume of substances to one another, both qualitatively and quantitatively. Again, same thing from last section, trying to carry out conversions between these types of things. Identify the number of elementary entities in a mole of any substance to calculate the molar masses of elements and compounds. Again, that's utilizing Avogadro's number as a conversion factor. Perform calculations involving moles, masses, and numbers of atoms, molecules, and formula units. Again, carry out those calculations. And then use the periodic table to calculate the molar mass of a compound based on its constituent elements. All right, start with molar mass. It's the mass in grams of 1 mole of a substance. So, molar mass of nitrogen, atomic nitrogen, 14.01 grams per mole. The molar mass of water is 18.02 grams per mole. The reason is you're taking 2 hydrogen atoms, each with an average mass of 1.008 grams, then 1 oxygen atom, 16.00 grams, simply adding those together. Do something a little more complicated. Barium nitrate, 261.35 grams per mole. It's because I'm taking the mass of 1 barium atom, 2 nitrogen atoms, and 6 oxygen atoms, and simply adding them all together. So let's see if you can do that. Which of the following is closest to the average mass of 1 atom of copper? Now, you're going to have to look up what the mass of copper is on a periodic table. It's not that hard to find one. A simple Google image search will get you one in about 5 seconds. Go ahead and press pause so you can find that mass and then carry out a conversion using Avogadro's number. All right, let's see what we did here. Boom. Correct answer is E. Now, a single atom of copper. That should clue you in that number should be very, very small. So even without doing any calculations, you really could have surmised that it was E times 10 to the negative 22 grams. That's an incredibly small mass. 1 atom. All right. This is a concept check I'm not going to give you the answer to. So if you want to check your work, because again, I please try this on your own. But if you want to check your work, you're going to have to communicate with your fellow classmates or with myself through some avenue to get the answer and double check that you did this correctly. Calculate the number of copper atoms in a 63.55 gram sample of copper. Another concept check. I'll give you the answer for this one. Please press pause so you can generate your answer. Which of the following 100.0 gram samples contains the greatest number of atoms? So if I have 100 grams of something, which one of these is going to have the greatest number of atoms? Correct answer is A. Magnesium is the smallest, or has the smallest average atomic mass, 24.3 AMU. And since, or should I say, out of these three options, since magnesium is lighter than zinc and silver, it will take more atoms to reach 100 grams. All right, this is one where you will not get the answer, so you're going to have to communicate with your classmates or myself in some other avenue. Rank the following according to number of atoms, greatest to least. All right, I'll give you the answer for this one. Please give it a shot. Consider separate 100.0 gram samples of each of the following. We have H2O, N2O, C3H6O2, and CO2. Rank them from greatest to least number of oxygen atoms. If you have 100 grams of each of these four things, which one is going to have the most oxygen atoms? Go ahead and press pause now so you can generate your answer. All right. H2O has the largest number of oxygen atoms. It has 3.343 times 10 to the 24th oxygen atoms. Carbon dioxide coming in second with 2.737 times 10 to the 24th oxygen atoms. Third place is C3H6O2 coming in with 1.626 times 10 to the 24th oxygen atoms. And coming in last place in 2O coming in with 1.368 times 10 to the 24th oxygen atoms. All right, so get an idea of where we're going. I'm going to read the problem and then decide on the final goal, meaning what am I supposed to come up with? Am I supposed to come up with a number of formula units, a number of atoms? Am I supposed to come up with a molar mass? Am I supposed to come up with a volume? Understand what the question is asking you for. Then ask, how do I get there? One of the best things that you can do in this course is work backwards from your final goal. All right, go to where you're trying to go. You just identified that you need to calculate, your answer needs to be in grams per mole or whatever. Reason backwards. That can help you get an idea of the path you're supposed to take to that final answer. Then lastly, give yourself a reality check. Does that answer make any kind of sense at all? Is it reasonable? Is it wildly outlandish, or does it kind of make sense? You can kind of broad strokes check your answer. And I strongly suggest you make a habit of that throughout this course. It will save you a lot of headache, a lot of stress, and in the long run, it'll actually save you time.